Hello grade 12, this is Physical Science. My name is Gillian, and today we are looking at the big ideas of this wild topic, acid and bases, and how it fits in with equilibrium. So today what I want to do is quickly revise acids and base theory, and then head into that really complicated a big idea of hydrolysis. So have a look at my screen. Let's see where we've come from, our grade 11 work. So acid-base theory started off with Arrhenius in the 1800s, and he came up with his own theory. We're going to have a look at it in a moment. His theory had limitations, and so two guys who were working on opposite sides of the earth, Bronsted and Lowry, they came up with, can you believe it, the same theory simultaneously. And so we're going to have a look at their theory as well. Part of this is knowing what ionization is, knowing what dissociation is, and working out conjugate acid-base pairs. So we will look at that too today. Now, types of reactions that we have in the acid-base section, there are 4 of them. And so neutralization is one that comes up really often, and that is an acid and a base reacting together. Then we have got 3 others, with an acid reacting with a metal oxide, an acid reacting with a metal carbonate, and an acid reacting with a metal. Now, all 4 of these reactions produce salts, not as table salt that you put on your slap chips or your food, but a chemical salt, so an ionically bonded substance. Now, pH scale. pH scale is also really important, and we deal with pH scale in quite a bit more detail in grade 12. Now, we don't have time for that today, so I'm hoping you're going to join me on my consolidation lesson, because we're going to dive into the pH scale and how to use logarithms to solve for pH. Okay, so let's have a look at our acid-base theory and Arrhenius. So Arrhenius only looked at acids and bases in the neutralization reaction. So neutralization is an acid and a base reacting together. Okay, so that was one of his limitations. It was only dealing with this neutralization reaction. He also looked at it in one solvent, and that solvent was this aqueous solution, so it was in water. So he only looked at what was happening with acids and bases in water, and so this was another limitation, that he only viewed the solvent as being water, even though there are other solvents. So what did he come up with? What he said was a base was a substance that produced a hydroxide ion, and that's called our hydroxide ions, the OH minus ion. He said that an acid was a substance that produced the H plus ion, the hydrogen ion, or another way that we know of it is this hydronium ion, that ion there. So what were his limitations? Well, as I've said, the solvent that he used was water, and so he couldn't explain acids and bases in a different solvent. And the other thing that he couldn't explain was substances that are bases that don't produce this hydroxide ion, and so there were definite limitations to his theory. So there needed to be a theory that encompassed a lot more of the other substances, and that's where the Bronsted-Lowry theory comes in. So Bronsted-Lowry is a theory that speaks about protons. So if we have a look at this hydrogen hydrogen atom that I've got on the screen, hydrogen has got 1 proton and it has 1 electron. Now, when that electron is given away, we sit with a naked hydrogen ion. It has nothing to protect it. It is just purely a single proton. And so their theory is talking about this substance, the H plus ion, and it is known as a proton, one single proton. So an acid is a substance that is going to give a proton away. A transfer of protons, that's what we're talking about here. So an acid gives a proton away. It is a donor. What about a base? A base is a substance that then takes on that proton, and so it is known as the proton acceptor. There is this transfer of protons in this reaction. It is a transfer of protons, and the whole process is called protolysis, or this reaction is called protolysis. Protolysis, the transfer of protons. What is the proton? The proton is the H plus ion. We know it as the proton. Now, we do have lists of acids and bases that are weak and that are strong. And it would be in your interest to learn these off by heart so that you know when you come across these acids and bases which ones are strong and which ones are weak. So I've put a list up here. We've got hydrogen chloride or hydrochloric acid. We've got sulfuric acid. We've got nitric acid. We've got hydrobromide. There we go, the hydrobromic acid. We've got the hydroiodic acid, and this one is an interesting one. It is hypochlorite. Hypochlorite. That po maybe helps you remember that there's oxygens involved in this one. The one at the top is hydrochloride. This one is hypochlorite. These are all strong acids. What about weak acids? Well, we've got this acetic acid or ethanoic acid. We know it as vinegar. You do put it on your chips. You can eat it. Oxalic acid is another one. There's one that I haven't put here, and this is the carbonates, the hydrogen carbonate. So that's carbonic acid. Know those. What about bases? Well, the bases that are strong all have this hydroxide ion, sodium hydroxide, lithium hydroxide, potassium hydroxide, calcium hydroxide. You can see that there's a 2 there, and that's because the calcium and the barium come from group 2, and so they have got a charge of 2+. There's one that's not there, and it might be an exception. So that is magnesium hydroxide. Now, magnesium hydroxide is actually a weak base. So learn that one. Another one which is a very interesting substance, and that is ammonia. Now, ammonia is covalently bonded, and we would expect it to react like the rest of the acids, these acids here, because they are covalently bonded, but it does not. It is a weak base. So this is an exception. This is a rebel. It is a weak base. The metal carbonates are also weak bases, and there's another one which is the metal hydrogen carbonate. So we will come across those, and you will come across those in questions. Make sure you learn them. What about the conjugate base pairs, the acid-base pairs? This is all about the accepting of the proton and the giving of the proton away. So how do we define the acid, and how do we define the base in terms of the Bronsted-Lowry theory? So if we look at this weak acid, it is carbonic acid. Why do we call it an acid? Because it is going to give a proton away. It gives just one proton to the water in this case. So this is ionization. It is an ionization reaction. And we can see on this side that the product is that it has given a proton away. It is 1 hydrogen plus ion less. And it forms that ion. So this is an acid because it is donating a proton. If we have a look at the reverse reaction, so we read it then from the other way around. We read it from the right side to the left side, we see that to form this product over here, it is going to have to take on a proton from this hydronium ion. That means it's acting as a base. Okay, it's acting as a base. It's taking on the proton. So this is what we would call the conjugate acid-base pair. They are linked. If we read from the forward reaction from the left to the right, we see that the carbonic acid is an acid, and if we read it from right to left, the reverse reaction, we see that this substance is going to act as a base. What about the water in this case? Well, the water is taking on the proton, so it is the base in the forward reaction. And what about the reverse reaction? Well, it's donating the proton, so it is going to be the acid. So this is the second conjugate acid-base pair. You will notice that the arrows are different lengths, and that is showing you that this substance, the carbonic acid, actually likes being in its molecular state. It likes being over here rather than in its ionic state, and so it will the equilibrium will lean to that side. It prefers to sit closer on the reverse reaction in its molecular form rather than in its ionic form. Right, ionization, grade 12s, ionization. Ionization is the reaction of a covalently bonded particle or molecule with water and a formation of ions. So when we have an acid which is reacting with water and it's a strong acid, it is going to ionize completely. It means that that reaction, there's very, very little of this molecular form of acid left in solution. It really does like being in this form here, and you'll see that the arrow is only one arrow because this lies completely to the right-hand side, and the acid in this case ionizes completely. It really loves being a hydronium ion rather than being in its molecular form. So when we have complete ionization, we have a strong acid. We have got a high concentration of hydronium ion and chloride ion in solution. It means that our Ka value, so that's like the equilibrium constant just for acids. So that Ka value is going to be high. It's going to be greater than 1. Why? Because there is a high concentration of hydronium ions and chloride ions in solution. So it means that there is a high conductivity, and that this solution, these ions have the potential to react well, so a high reactivity. That's what makes a strong acid. Right, we are going to take a break. When we come back, we're going to look at what is a weak acid. Hello, grade 12s. Welcome back from the break. We are now going to look at a weak acid. So what happens with the weak acid? Well, it loves being in its molecular form. It really doesn't like ionizing into its component ions, and so there really are many more molecules in solution than there are this hydronium ion and the negative ion. So this is acetic acid. We also know it as vinegar. So acetic acid is it's known as a weak acid. And the reason why it's known as a weak acid is because it likes being in its molecular form. And you can see here the arrows are showing you that that's where the equilibrium lies. There are many, many more of these full molecules in solution than there are of the hydronium ion and of the acetate ion. And so the Ka value is going to be low, and it's going to be less than 1. So it has got a low concentration of ions in this form. It means that the conductivity is going to be low and it's not going to react that well. So what about a weak acid? It has got incomplete ionization. Incomplete ionization, whereas a strong acid is complete ionization. The same theory applies to a base. A strong base is going to dissociate completely. Dissociation, because they are generally ionically bonded. You can see here sodium hydroxide is a really strong base. What does it do? It loves being in its ionic form. There we go. It forms a high concentration of hydroxide ions. This is the hydroxide ion in solution. So there are the concentration of those hydroxide ions is high, conductivity is high, reactivity is high, and the Kb value is going to be greater than 1. Again, that Kb value is talking about the base, about how many hydroxide ions are in solution, and we call it Kb. So it's like the equilibrium constant. Now, this magnesium hydroxide, we would think is a strong base, but it is not. It does not like being in its ionic form. It likes being, there we go, as a whole substance, and so its equilibrium lies to its complete form. Magnesium 2 plus and the 2OH minus ions are low in concentration. What about this? The extent of dissociation is poor. It does not dissociate completely, whereas the sodium hydroxide does. So sodium hydroxide is strong. Magnesium hydroxide is a weak base because its extent of dissociation is poor. It is incomplete dissociation. It means that its Kb value is going to be less than 1. It is going to have low conductivity and low reactivity. Why? Even though it says 2 OH minus ions, the concentration of those ions is very low, and so its Kb value is going to be low. What about, we've got strong and we've got weak, we've sorted that out. Now what about concentrated and dilute? Well, dilute and concentrated is talking about a volume. Strong and weak is talking about the degree of dissociation or the degree of ionization. So I have got 1 mole of both a strong acid or base and 1 mole of a weak acid or base. And you can see here that the number of ions in solution is high. So it will be a high number of ions in solution for a strong acid or base. In a 1 mole of a weak acid or base, you can see that there are very few ions in solution. The number of ions is very low because the dissociation and the ionization is incomplete. Now, what happens if I add water? What happens if I dilute it? So I increase the solvent. You can see that the volume increases, but the number of particles or ions in solution doesn't. So we still have a high number of ions in solution for a strong acid or base, whereas a weak acid or base, you can see the same amount of solvent, you can see there, so we're comparing correctly. You can see that the number of ions in solution is very low. So even if we dilute a strong acid or base, it's still going to be strong because ionization is complete. With a weak acid or base, if we dilute that, it's still going to be weak because there are very few particles or ions in solution, incomplete ionization or dissociation. We have to be careful though that we are comparing correctly. So you can see that my comparison is fair, 1 mole versus 1 mole, and you can see that the amount of solvent is the same over here. I hope that helps you, grade 12s, with the concept of strength versus concentration and dilution. Right, grade 12s, it's heating up here. There are 2 more topics that I would love to cover in this time. The first one is titrations. So we're going to have a quick look at what those are. And then the other one is hydrolysis. So let's skip on to titrations. So titrations revolves about a single reaction, and that reaction is neutralization. It is a salt-forming reaction with an acid and a base. So an acid and a base, when they react together, they form a salt and water. Now, titrations, that's a big word. We need to know what it is. It is the name for a technique that we use in the laboratory, and it involves specific equipment. So you can see in my picture here, we have a pipette, we have a burette, which is a weird instrument. It's like a long straw with a tap on it, and we can regulate how we run the liquid in the top through down to the bottom. We have a conical flask, and we put one substance in the burette, let's say the base, we can put into the burette, and we put the acid into the conical flask. It can be the other way around, but these substances generally are see-through. We can't see them. So we will never know when this reaction reaches neutrality, when the acid will neutralize the base or vice versa. So we need to add in there an indicator. And the indicator is really important when we are doing calculations. There are 2 words that you need to know. The one is endpoint. Now the endpoint is where the indicator actually changes color. Now there are 3 colors for the indicator, 1 in the base, 1 in the acid, and then there's a slight change in the indicator color as this endpoint is reached, and that you need to be quite precise about, and you need to look at it, good observations with your eye to check where that endpoint actually is. The equivalence point is the other word that you need to know, and that is where that's talking about the chemical reaction. And equivalence point is where the acid completely reacts with the base, or vice versa, where the base completely reacts with the acid. So now we delve into this chemistry in more detail when we're speaking about hydrolysis. So the titration has happened, the neutralization reaction has happened, and now we get the product, which is salt and water. And we're going to look at what happens with that salt. So that salt, the results, the product of this neutralization reaction, reacts with the water. And we can have hydrolysis happening. This is the official definition for hydrolysis. So a salt can hydrolyze, there we go, with water, which may cause a change in the pH of the solution. When we titrate a strong acid and a strong base together, we know that the pH at the end of this reaction is 7 or around about 7. And that explanation is given very nicely in the videos that have been preset for you to watch. So I'm not going to go into that. But what I do want to do is have a look at where we have acid and base that are not of the same strength. When we've got a strong acid and a weak base, and a weak acid and a strong base, what happens? So here's an example of a strong acid and a weak base. We have the salt forming, which is ammonium chloride. Now, when we want to see what the acid is and what the base is, we look at the ions of this particular salt. So we've got the NH4 plus ion, which is the ammonium ion, and we have the chloride minus ion forming. So the anion is the chloride minus ion. That comes from the acid. So what acid will give us a chloride ion? It would be HCl, and we know that that is a strong acid. What about the base? Well, ammonium must come from ammonia, and we know that ammonia is a weak base. Now, what happens when we take the salt and we put it into the water that has formed? There is going to be some dissociation into these ions, the ammonium plus ion and the chloride minus ion. Now, we know that the ammonium comes from a very weak base, which is ammonia. That's weak. It's the weak base. So its conjugate pair is going to be a strong acid. So that's the ammonium ion is going to be a strong acid. Chloride minus ion, that comes from a strong acid, and therefore it is a weak base. So it is not going to do anything. It likes being in that form. Weak base means taking on a proton. It's not going to do that. It's weak. It likes being in its ionic form. But what about this ammonium ion? So the ammonium ion is a strong acid, which means that it is going to give away its H plus ion, its proton. It's going to give it away. And so this solution, resulting solution that we're going to have is going to be slightly higher in the proton concentration. So its H plus concentration is going to be slightly higher, and that is going to affect the pH, and so it gives us a pH that is slightly acidic. So when we have a strong acid and a weak base that are neutralizing each other, the resulting salt is going to be slightly acidic. It's an acidic salt that is formed, and that solution, resulting solution, is going to be slightly acidic. The pH is then going to be just below 7, just below 7. So the pH in this case, the pH is going to be a little less than 7. What happens when we have a weak acid reacting with a strong base? Now, here's a salt, which is the acetate, the sodium acetate salt. And again, we're going to have a look at the ions. So this is the negative ion. This is the really weird way of writing it. The organic chemists like writing things the opposite way, and so it makes us a little bit confused. But we can handle that. So the acetate ion is the negative ion, and so that is going to be, that's going to come from the acid. So this will be acetic acid, vinegar, or that CH3COOH. The cation is going to come from the base, that's sodium, so it's going to be sodium hydroxide. Okay, so we know that that is the strong base. This we know, the vinegar, we know is a weak acid. Now what happens when we have a look at the products? So this salt is going to dissociate or ionize into its component ions. We know that this comes from, the acetate comes from, is a weak acid. Okay, it comes from a weak acid. The acetic acid is weak. Therefore, its conjugate base is going to be strong. So here's the conjugate base, the acetate ion, and that's going to be strong. What does it mean? It means that it's going to grab onto those protons. The H plus ion is going to grab onto it. Why will sodium not participate? Why will it be quite happy? Well, it comes from a very strong base, so it is a weak acid. it's not going to be wanting to do anything. So it stays in its ionic form, but this acetate ion is a strong base. It wants to grab onto those protons. It takes those out of solution, and so we end up with quite a high concentration, well, not quite a higher concentration of the hydroxide ion. That means that this salt, which is formed, is a slightly basic salt, and it forms a slightly basic solution. So the pH of this solution is going to be a little bit higher than 7, just a little bit higher than 7. So on my screen, I have the overview, which you've probably seen before with big ideas. But what we want to really look at now is the pH scale. So we want to have a look at that and how we ask those sort of questions. And then neutralization is something that comes up often, particularly when we are trying to solve problems using our knowledge of stoichiometry. So this is quite tricky, it can be quite tricky, so we need to know our facts really well. So let's have a look at our first question. Question 1 is about ethanoic acid. Now, it says ethanoic acid, and they give us the formula for ethanoic acid, is an ingredient of household vinegar, and that should give you a heads up. So this is vinegar. Acetic acid or ethanoic acid is the same as vinegar, and we should know it as a weak acid. What does that mean? A weak acid is a substance which does not ionize completely. It really prefers to be in the molecular form. And that's actually the first question that says, is ethanoic acid a weak acid or a strong acid? And so we're going to say it is a weak acid. And what reason are we going to give? Well, we need to say that in particular this acid, so you can either use the formula or you can use the name ethanoic acid, does not ionize completely. So it does not ionize completely. We could also say that it has incomplete ionization. Okay. So that is what distinguishes a weak acid from a strong acid. A strong acid, of course, ionizes completely. And so there's very, very, very little molecules left in a solution of a strong acid. The next question is, an ethanoic solution has a pH, right? This is the first time we're coming up with pH, and it is at a very specific temperature, 25 degrees Celsius. We'll come back to that. Then calculate the concentration of hydronium ions, which is this ion here, H3O plus, aqueous in the solution. Now, this gives me the opportunity of walking you through this pH scale. So let's have a look at this. So when we look at the pH scale, it's a scale to place substances in terms of the H plus content. That's what this H is talking about. So how much of that ion is present. And to get a standard, water was used. So water is considered to have a pH of 7. So there is an auto-ionization of water, that reaction, where the water can act as an acid and as a base. So let's have a look at this. We see that we have the hydroxide ions and the H3O plus ions that are being produced in this reaction. So one of these water molecules is going to act as a donor, and I'm just going to take this first water molecule. Oops, it's a bit skew. And that water molecule is going to donate a proton, a H plus ion, to the second water molecule. That makes this one the acid because it is a donor, and it makes the second water molecule a base because it is accepting that proton. So here we have, in that process, we then have the hydronium ion, which is this one here, and the hydroxide ion being formed. You can see that our arrows are showing that there is chemical equilibrium and that the chemical equilibrium prefers the reverse reaction. So the very few water molecules actually react with themselves to form these ions. The water molecule prefers to be in the molecular form and not the ionic form, and that is why the reverse reaction arrow is bigger, longer than the forward reaction arrow. But out of this, we can calculate the Kc. Now, you've heard about the Kc, the equilibrium constant, and that is, I've written the formula here. It is the concentration of the product ions, so the hydronium ion and the hydroxide ion. So the concentration of those two times together divided by the concentration of the water molecules. Now, the water molecules will have a concentration of 1 because they are in the liquid form, and so they don't impact this formula. And we end up with a formula that is just the concentration of the hydronium ion times the concentration of the hydroxide ion. We call this Kw. Okay, because we're now working with water. So it is the equilibrium constant specifically of water, and it has to be at this temperature because our equilibrium constant is changed with temperature. It's the only thing that changes the equilibrium constant. So this has to be at a constant temperature. We end up with an answer of 1 times 10 to the minus 14. Now that minus 14 is telling you that ion concentration in a solution is very, very small. It's little. Because we are going to have an equal number of hydronium ions to hydroxide ions, we can say that the concentration of the two is the same, and it will be 1 times 10 to the minus 7. Now these are inversely proportional. That means that if the hydronium concentration decreases, the hydroxide concentration is going to increase by the same amount. Okay, so that's what's going to happen. If the one decreases, the other one is going to increase. How do we end up then with this scale? Well, we find that water, when we have equal number of ions, is 1 times 10 to the minus 7. And if we use a logarithm to change that around, and here it is here, we will find that if we take the hydronium ion, that the pH is going to equal 7. So this is a really important formula for changing a concentration into a scale, into a number that we can work with. And there's the logarithm. Now, when we speak about the ionization constant, the ionization constant is when we're talking about acids that are ionizing in water. We have a Ka value like that. Okay, so it's the ionization constant. When we're talking about something which is dissociating, it's invariably about a base, and so its Kb is going to be the constant for the base, the equilibrium constant for the base. We call it the dissociation constant. If we've got a strong ionization happening, complete ionization, then our answer there, the ratio is going to be greater than 1. And if we have a Kb value which is greater than 1, then we know that our ionization is happening to completion. We're dealing with a strong base. Grade 12s. Let's get back to our question. So we are given a pH of 3,85. at this particular temperature so that we know that we're dealing with an equilibrium constant at the correct temperature. Calculate the concentration of these hydronium ions in solution. We're going to use that equation that we have just seen. So it is the logarithm, pH is equal to minus log of the concentration of the hydronium ions. We know what the concentration is. We know what the pH is. It is 3,85, so we're going to substitute that in. And we're going to, on our calculators, do our logarithm working out, and we end up with an answer of 1,4 times 10 to the minus 4 mole per decimeter cubed. Now, concentration is mole per decimeter cubed, but have a look here at that exponent to the minus 4. So that is telling us that that it's a little bit. There is not a big amount of ionization. If there was a big amount of ionization, then that would be to the power of 0 or 1 or 2 maybe, and then we minus 2, minus 1. And then we know that our pH is 0, 1 or 2, and we're dealing with a strong acid. But we're not dealing with a strong acid. This is ethanoic acid. It is a weak acid. It ionizes incompletely, and so this number here is correct. Minus 4 to the minus 4, and it shows us in our pH value, so that's 3,85. It means that we haven't got such a strong acid. The pH is closer to 7 than it is to 0. Let's move on to our next question. Sodium ethanoate, and here's the equation as the formula for it. That is the negative part of this compound, and that is the positive part. Forms when ethanoic acid reacts with sodium hydroxide. So ethanoic acid, we know, is a weak acid, and its formula is going to be CH3COOH. There we go. That H plus tells us that it is an acid. Sodium hydroxide, we know, is a strong base, and its formula is NaOH. Now, this is the salt. Sodium ethanoate is the salt that forms when we've got this weak acid reacting with a strong base. The question is, will the pH of the sodium ethanoate solution be greater than 7, less than 7, or equal to 7? Well, we know that we have a weak acid and a strong base. There's no ways that our pH can be 7. Why? Because to get a pH of 7, we need a strong acid and a strong base. And then the resulting salt is going to have, it's going to be a neutral salt that is formed. Our solution will be neutral. So we're going to have to cross that one out. That one's not going to work. So now let's look at our weak acid and our strong base. If we have those two reacting together, we're going to end up with a salt that is slightly basic. Slightly basic. In other words, the pH is going to be a little bit more than 7. Not a huge amount more, just a little bit more. So our answer here is it's going to be greater than 7. It's time for a break. When we come back, we're going to have a look at the chemistry of why this pH is greater than 7. Welcome back from the break, grade 12s. So we have just said that when we have neutralization, a neutralization reaction of a weak acid and a strong base, the salt that results is going to be slightly basic. So now we have to prove or write an answer to why. why is this happening? So this question, 1.1.4, says, explain the answer to question 1.1.3 with the aid of a balanced equation. Right, so I've written down what's happening in our reaction flask. So we have got this salt, this sodium acetate that has formed, and it is going to break up into its component ions, and there we've got the one ion there and the sodium plus ion there. This comes from a weak acid, so this part comes from a weak acid. That means that its conjugate base is going to be strong. So this is a strong conjugate base, right? That means that this ion is going to be hungry for protons. So it is going to be really keen to pick up this proton here that is available from the water, the ionization of water. And so how can we show that in our balanced equation? So we're going to write CH3COO minus aqueous plus H plus. And that's going to form CH3COOH. It likes being in that molecular form. But what else do we have here? We have OH minus. And so the OH minus ions are going to be in solution. The H plus ions have been removed from solution by this reaction. In terms of Le Chatelier, what's going to happen is there's going to be a stress on the system. The equilibrium is going to try and address that stress by making more H plus ions. So the equilibrium is going to favor the forward reaction. By favoring the forward reaction, more hydroxide ions are going to be made as well as H plus ions. And because there are a lot more hydroxide ions being made, that pH is going to be greater than 7. So that shows you what is happening in this particular reaction. So the salt that is formed from a strong base and a weak acid is going to give you a salt which is slightly basic. Let's continue. This question is fun. I love this question. It's a whole lot of stoichiometry all thrown in with our knowledge of acids and bases. So we are given an element X which is unknown. And this learner wants to identify what element X is from this compound, XHCO3. So we recognize this as a carbonate, a hydrogen carbonate. So what is that going to be? So a hydrogen carbonate, if we think back to our list from the big ideas, is going to be a weak base. How does she do this? How does she carry out this experiment? She dissolves 0.4 grams of this unknown X substance in 100 centimeters cubed of water. I'd like to highlight that for you. So we know that when we're speaking about volume, we're speaking about decimeters cubed. So these values, if they are given to us in centimeters cubed, have to be converted into decimeters cubed. She then titrates, okay, so the word titrates, we know that this is a technique when we take an acid and a base and we titrate them together and there's a neutralization reaction. All of this solution with 0.2 moles per decimeter cubed of hydrochloric acid. So we know that HCl is a strong acid. Okay, so what's happening here? We've got a titration happening. I'm going to draw a little picture so that I can sort it out in my mind. Let's say that she puts the acid in there, and that's HCl, and that's a strong acid. And then in her conical flask, she has got a solution here, and it is of this XHCO3, and that is a weak base. She uses an indicator methyl orange during this titration. Okay. The first question is, calculate the pH of the hydrochloric solution. Well, that's easy. We know how to do that. We're going to use this formula, and we are going to check out what the concentration is that they give us. So they give us a concentration of the hydrochloric acid being 0.2 moles per decimeter cubed. That's easy, that's all we need. So we're going to substitute that in to our equation. We use our calculators to find the logarithm, and we come up with an answer of 0.6999, which we can round off to 0.7. Is that the correct answer? Let's check. Well, hydrochloric acid is a strong acid. That means it needs to have a pH between 0 and 2. Is our pH between 0 and 2? Absolutely, it's 0.7. That means that the hydrochloric acid is a strong acid. So we've got the correct answer. Let's carry on. Give a reason why methyl orange is a suitable indicator for this titration. Now, we've got three kinds of indicators. We've got bromothiamyl blue, we've got phenolphthalein, and we've got methyl orange. Bromothiamyl blue is an excellent indicator to use when we've got a strong acid and a strong base. Why? Because the end point is around about 7-ish. And that is where neutralization happens for a strong acid and a strong base. But when we have a weak acid, strong base, and a strong acid, weak base, our endpoint doesn't lie there. We've discussed this, that when we've got a strong base with a weak acid, the salt that is going to result is going to be slightly basic. And so the endpoint is going to be just bigger than 7. So if we look here at phenolphthalein, we see that its endpoint is bigger than 7. So that we would use when we have a titration of a strong base and a weak acid. But for this particular reaction, we have HCl, which is a strong acid. What does that mean? It means that the salt that results is going to be slightly acidic. So will our endpoint be lower than 7? Let's check it out from the table. Yes, it is. It's going to be lower than 7, and so this is the correct indicator to use. Give a reason why it is a suitable indicator, methyl orange, for this particular reaction. Well, we need to say that we're using a strong acid and a weak base in this neutralization reaction, and so the end point is going to have a pH which is less than 7. Okay, now 2.1.3. At the end point, she finds that 20 centimeters cubed, again we've got the centimeters cubed, of the acid neutralizes all of the hydrogen carbonate solution. So this is telling us that the HCl is in excess. So if all of the hydrogen carbonate solution is used up, it means that the acid will be in excess. There's a balanced equation, it's given to you, and we have to identify the element X here. Now, the only way we can identify the element X is by finding out its relative atomic mass. That's the only way we can do that. So our end goal is to find the mass. What do we have though? We've got concentration of HCl, we've got volume of HCl, which has been converted into decimeters cubed. And we have got an initial mass of this unknown solution, unknown substance, the hydrogen carbonate substance. And we also have got a ratio. So we're reacting the HCl, the acid, with this weak base, and the ratio is 1 to 1. So it means that 1 mole of hydrochloric acid is going to neutralize 1 mole of this basic substance. That's really good for us, this mole ratio. Here we go, here it is here. So we're going to find out how many moles of hydrochloric acid has reacted. We use this equation, C is equal to N over V. You find it on your data sheet. We substitute in the values. We know that the concentration is 0.2 of the hydrochloric acid. We know that the volume that was used is 0.02, and we end up with an answer of number of moles is 4 times 10 to the minus 3. So we're now going to calculate the mass, not the atomic mass, but the molecular mass of this unknown substance, which is the XHCO3, because that's the thing that's reacting, right? So we pop it into this formula again from our data sheet. We know the number of moles because the ratio is 1 to 1. We know how much mass is being used. We were told it's 0.4, and we end up with a molar mass of 100 grams per mole. That is of the entire substance, XHCO3. Now we've got to find out what is the X, just the X. So we are going to calculate the molecular mass of this whole thing. We get from our periodic table the 1, the 12 for carbon, the 48, which is 16 times 3, and we find out that the rest of that molecule or substance is 61. If we work that around, we end up with a mass for X of 39 grams per mole. And if we check our periodic table, we will find that that is the atomic mass of potassium, and we have solved our problem. Right, grade 12s, that's all we have time for today. I hope to see you next time.